let's get into it. It's 5 o'clock. So the title of this section is the Gram-Schmidt algorithm. We're probably not actually going to get around to proving that today. We'll see how we go. But we're going to sort of head in that direction. So the Gram-Schmidt algorithm, or the Gram-Schmidt theorem is, I guess, the more interesting object. The Gram-Schmidt theorem tells you that every inner product space, at least finite dimensional one, has an orthonormal basis. Okay? So what is an orthonormal basis? An orthonormal basis is a basis for your space that satisfies two properties, right? So every vector in it is a unit vector. So every vector has length 1, and we know what that means if we're in an inner product space, because once you've got an inner product, you have a norm or a length function. And the other property is that every pair of vectors in that basis are orthogonal to each other, right? So it's just like a basis, except for, well, it is a basis, but it's a special kind of basis. For a basis, the property you care about is that every vector in your space can be written as a linear combination of things from that set, but the real characteristic is that it's independent, right? So nobody in that set is a linear combination of the other things in that set. So when we're talking about orthogonality, we have to be a little bit more careful, because our definition of orthogonality referred to two vectors, right? We know what it means for two vectors to be orthogonal. It means their inner product is 0. So what does it mean to say that the set is orthogonal? It means that every pair of things in that set is orthogonal, or are orthogonal, okay? So if you've got a set of n things in it and you say that set is orthogonal, it means every two things in that set that you pick out, you take their inner product, you get 0. Okay. So any non-zero vector in your set you can normalize by dividing by its length, okay? So provided you've got an orthogonal set of non-zero vectors, you can turn that into an orthonormal set very easily just by dividing everybody by their length. All right, so here's an example. We've got this set S, and the first question is this set orthogonal in Euclidean space? So to check if it's orthogonal, what do? We're in Euclidean space, so we care about dot products. You just take every possible inner product. All right, so you pick every possible pair out of this set. We've got 3 things. You want to pick all possible pairs. So there's 3 ways of doing that. And if you just crunch those out or stare at them, you'll see that, yes, they're all 0. So S is orthogonal. Right? That's what we mean when we say S is orthogonal. It means you take any pair of vectors in that set, S, take their dot products, you get 0. So every pair is orthogonal. If we want to know whether it's orthonormal, we've got to compute the lengths of everybody. So the length of this thing is 1 plus 1 plus 1 square rooted, so that's root 3. So that thing is not a unit vector because it doesn't have length 1. So the answer is going to be no here. The length of the second one is root 2. And the length of the third one, all right, because we're using the dot product, is 4 plus 1 square rooted, so that's root 6. So S is not orthonormal. But it's very easy to make an orthonormal set out of S by just dividing everybody in S by their length. So if we take 1 on root 3, 1, 1, 1, and 1 on root 2, 0, 1, minus 1, and 1 on root 6, 2, minus 1, minus 1, we've got an orthonormal set. Okay? Everybody happy with that? All right, so that's how you check orthogonality and then how you normalize a set of vectors. Okay, so when we were talking about orthonormal sets last week, we observed that there were independent pairs of vectors that weren't orthogonal. But what I want to claim now is that the converse is not true, with one caveat. If you've got an orthogonal set of non-zero vectors in whatever inner product space you're playing with, then it has to be independent, right? So provided all your vectors are non-zero, orthogonality implies linear independence. Converse is false, but as long as you're talking about non-zero vectors, orthogonality implies independence. So for instance, as a corollary, if you know you're in an n-dimensional space and you can write down an orthogonal set of n non-zero vectors, you have a basis. Okay? And orthogonality is often a little bit easier to prove because you just have to compute inner products. And usually computing inner products is pretty easy. You don't have to take your big n-dimensional linear independence equation and count how many solutions you have when you set some linear combination equal to 0. Right? You can just compute inner products. All right, so why is this true? Well, we want to make a statement about independence. By definition, independence is the statement that that equation is only going to hold when all the CJs are 0, right? So we're going to have to somehow use orthogonality of our set of vectors to show that all the CJs are 0. Now, the only thing that we know about this set, well, I guess we know two things. One is that all these vectors are non-zero. The more interesting thing is that it's an orthogonal set, right? So you take the inner product of anybody in that set with any other distinct thing in that set, you're going to get 0. Now, that's what we know. What we want to show is all the CJs are 0. So somehow we're going to have to use the fact that we know how to compute inner products of VI and VJ to learn that all the CJs are 0. Right? So we're going to have to take the inner product of something and something else if we're going to learn anything about the CJs. So this is the equation that we're starting with. So it would make sense, and basically the only thing that we could conceivably do is take the inner product of both sides of that thing with some vector and see what happens. So what would be a good candidate of what we should take the inner product of the left and right hand sides of that thing with, so that we learn something about the CJs? The stuff in S, yes, that would be right. That would be a very sensible thing to do, right? Pick something in S and take the inner product of the left and right hand side with this equation, with that thing in S, okay? So let's let I be something between 1 and n. So let's pick VI, right? So take an arbitrary thing in S. You take the inner product of VI with the left-hand side of this sum, of this equation. You have to get the same thing as if you took the inner product of VI with the right-hand side of the equation. But what's the inner product of VI and 0? 0, right? Because inner products act linearly, and any linear transformation acting on 0 gives you 0. The inner product of VI and 0 is 0. And we can simplify the left-hand side, right? Because, again, with VI fixed, inner products act linearly in the second argument, and linear transformations preserve linear combinations. So you can drag out that sum and all of the scalars out the front of the inner product. And what do we get? We get that sum over the j's, Cj, inner product of Vi and Vj equals 0. Sorry, that's not a vector 0, that's the number 0. That make sense? So it's just using linearity in the second argument, which is one of our vector inner product space axioms. Now, what's this thing? So one of them's an I, one of them's a J. Times Ci. Yeah, so the whole thing is that, yeah. 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 So if I look at just one of these isolated VI, VJs, it's going to be 0 for every J other than the ith one, right? Because this is an orthogonal set. So VI, VJ, if J is anything other than I, inner product of VI and VJ is 0. Unless I equal, well, say it more clearly, unless J equals I, right? So what's the left-hand side? The left-hand side is Ci, inner product of Vi with Vi. And that's 0. And as we just mentioned, the inner product of something with itself is the length squared. So you can write this like that if you like. Now, so far we've just used the orthogonality of the set S. We haven't used the fact that these are assumed to be non-zero vectors, but we're about to need that fact, right? So we also have the fact that none of these things are 0. And what does that mean? It means they've all got strictly positive length. Okay? So if we didn't demand that all of our vectors were non-zero, we still couldn't learn anything about the CIs, because maybe it's the VI squared, length of VI squared, that's sending this thing to 0. But if we demand that none of our vectors are 0, then it has to in fact be that the Ci is 0. Right? So by assumption, none of the VI's are 0, so the Ci has to be 0. And that holds for every single Ci. So we have an independent set. Okay, does that make sense? So every orthogonal set of non-zero vectors is independent. And as an immediate corollary, that means every orthonormal set is just immediately independent, right? Because if you're a unit vector, you're not the zero vector. Because if you're a unit vector, you have length 1, which means you don't have length 0, so you're not the zero vector. So if S is orthonormal, then the length of VI is 1, so VI is not 0. So S is an orthogonal set of non-zero vectors. Okay. All right, so that's the relationship between orthogonality or orthonormality and linear independence. All right, so the following result is not amazingly useful, but it's kind of cute, and it is, well, I guess it is sort of practically useful. And what it says is, in the same way that we know you can map abstract vector spaces down to Rn by using coordinate vectors, and that's an isomorphism, right? So you can sort of replace your abstract vector space by something very concrete, Rn, by using coordinate vectors, and we can replace our linear transformations, very abstract linear transformations, by something very concrete, matrices, by taking matrix representations, and those matrix representations act on coordinate vectors. So we've seen for vector spaces and linear transformations, we've got this process of taking the abstract thing and replacing it by coordinate vectors. You can do the same thing for inner products. So on any abstract inner product space at all, right, you've got that n-dimensional inner product space. If you pick an orthonormal basis, right, so let B be an orthonormal basis for your space. If you write your vectors, right, coordinate vectors for your vectors with respect to that orthonormal basis, then computing inner products, these abstract inner products, is exactly just taking dot products, right, just Euclidean high school dot products of the corresponding coordinate vectors. Okay, so let's just replace the abstract thing on the left by just dot product on the right, where the dot product on the right is using coordinate vectors again. The only thing you have to keep in mind is that the basis you have to use on the coordinate vectors has got to be orthonormal with respect to your inner product, right? Which makes some sense. Otherwise, how on earth would that work? The basis has got to know something about your inner product. So by demanding that your basis is orthonormal with respect to your inner product, that gives it all the information it needs about your inner product to allow this to work. Okay? So this is fairly straightforward to prove. So let's give the things in B names. Let's call them W, W1 up to Wn. And we'll write U and V in terms of this basis B. So let's say U is this linear combination of the things in B, and V is, say, this linear combination of the things in B. Then what do we have? Well, let's just compute the inner product. Inner product of U and V then is inner product of this linear combination. Okay. Now I'm using J's on the second linear combination just so that I don't get confused when I do the next step. But I can use linearity in both arguments. So let's say we'll do it in 2 steps. So linearity in the second argument means I can do the following. So I keep the first argument fixed. Right, so this is linearity in the second argument. And then for each fixed value of j, I can use linearity in the first argument to drag out the I sub. That's linearity again. And now, the inner product of Wi and Wj, what is it? 0 if they're not equal. Yep. What else do I know?
If they're equal, then it's the magnitude squared.
And in particular, this thing is orthonormal. So what's the magnitude? 1, right? So here we know everything about these inner products. So unless I is equal to j, we just get 0. So we only have to consider the case that I equals j. And then the inner product is just 1. Okay? So this whole sum here just degenerates to alpha j. Right? N minus 1 of the terms are just 0. The only term that contributes is when I is equal to j. And then you've just got alpha j times inner product of Wj with Wj, but Wj is a unit vector, so you've just got alpha j. So we've just got alpha j beta j summed over j. And now, what's that thing? What does that look like? It's a dot product, right? It's a dot product of a vector where, of two vectors, one of them where all the entries are alphas, and the other one where all the entries are betas. But what are those vectors? Well, U looks like this. So if I made U's coordinate vector with respect to B, it'd just be a vector full of the alphas. And V looks like this. So if I took V's coordinate vector with respect to B, it'd just be a vector full of all the betas. So this is precisely just the dot product of U's coordinate vector with respect to B and V's coordinate vector with respect to B. Okay, there's no tricks here, it just falls out. Yep.
Just with like the linearity, like the two time we use linearity.
Yep.
Just in it generally, does it matter if you apply the first part of the
No.
part?
No. See, and if you're really comfortable with what you're doing, do both at once. That's fine. Yeah. I guess I just did the second one first because that's what's actually in the axiom. But because of symmetry, it doesn't matter. Okay, so there's some properties of orthonormal bases, right? If you have an orthonormal basis, then you can replace all of your inner products with just dot products of coordinate vectors with respect to that orthonormal basis. And every orthonormal set is linearly independent. So there's some nice properties, well, a characterization of orthonormality in terms of linear independence, and one nice property in terms of how to relate inner products to dot products. But we still really haven't explained why orthonormal bases are so nice compared with just garden variety bases. And I think the answer to that question is really this theorem. Right? This gives you a very practical reason why orthonormal bases are better than normal ones. Right? Better than garden variety ones. So we know if you've got any basis at all, you can take any vector in your space and you can write it as a linear combination of the things in that basis. And there's precisely one way of doing it. Right? So that's very nice. The basis generates your entire space in a well-defined, unique way. But finding the coefficients in that linear combination is kind of painful, right? How do you do it? Well, there's no better way of doing it, no more sophisticated way of doing it than just doing a bunch of Gaussian elimination, right? You take the vector you're interested in, you try to write it as a linear combination of these things, gives you this big linear system if n's big, and you've got to sit there and find all of the coefficients by doing Gaussian elimination. But if you've got an orthonormal basis, the coefficients are extremely nice. The coefficient of V1, if you're trying to write U in terms of this basis, the coefficient of V1 is just the inner product of U and V1. The coefficient of V2 is just the inner product of U and V2, blah, 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 blah. Okay? So the coefficients, when you're writing a vector in terms of an orthonormal basis, the coefficients are really simple. And this is essentially the main reason why we like orthonormal bases. So, how do we do this? Well, let's just, this is sort of similar to the proof that we did for independence. So let's let U be, well, it has to be, since B is a basis, I know I can express U as some linear combination of the elements of that basis, B. So let's just write it like that. And our job is to show that Cj equals the inner product of U and Vj. Now, the way that we're going to do that, essentially the only sort of strategy that's going to allow us to do that is basically the same strategy that we used for independence, is that we want to make some statement about these coefficients here. The only thing that we have at our disposal is the orthonormality of B, so we're going to have to take inner products of something, right? There's no other way that we're going to work out what these coefficients are other than taking inner products of something. And the only inner products that we actually know are inner products of the V's with themselves, right? So VI with VJ. They're the only inner products we actually know. So if I want to find out what the CJ is, I'm going to take inner product, or if I want to know what the CI is, I'm going to take inner product of U with VI and see what happens, right? If we're going to be able to prove this at all, this is basically the only way that's going to work, because the only thing I actually know is the inner product of VI and VJ. So let's just plug in U. You can use linearity, using it in the first argument here. So I've got inner product of VJ and VI. Linearity. Again, same story. What's the inner product of VI and VJ? It's 0 if j is not equal to I, and it's 1 if j equals I. So this is just CI. Right, so I've used this argument 3 times in 20 minutes. This argument is essentially the nice fact about orthonormal bases. Okay, so what have we learned? We've learned that the CI we were trying to find is just the inner product of U and VI. And so we're done. Okay? So this is the reason we like orthonormal bases. All right. Let's do a poll. So here is a set that we've already looked at, right? We've proved that it's orthogonal. Now, none of those things are 0. We've got 3 vectors in R3. It's an orthogonal set of non-zero vectors in R3, of 3 things in R3, so it's a basis. We've got a coordinate vector, we've got a vector, and we're trying to write the coordinate vector of that vector with respect to B. Right? So in other words, let's try and write this vector as a linear combination of the things in B. What are the coefficients? So we can use our previous theorem to express this vector as a linear combination of the things in B. Right? And we want to use the orthogonality of B to do this. If you didn't know B was orthogonal, you'd have to sit down to do Gaussian elimination, which is tedious. But because we know B is orthogonal, there's a nice way of computing or calculating or expressing this thing as a linear combination of the things in B. Okay, so see if you can crunch it out. And the one thing you need to always keep in mind is the previous theorem applied to orthonormal bases. Okay? Now this thing, as we've shown, is not orthonormal. You can make an orthonormal thing out of it, but it's not orthonormal. So how would you use the previous theorem to apply it to something that's not actually orthonormal? So the previous theorem says that, well, if you started with something that actually was orthonormal, right, which would be this basis normalized properly, then we would know how to calculate all the coefficients. All right, so if I took all of the V1, V2, V3 and normalize them properly, then the previous theorem applies. And in each of these, I've got two copies of the length, or two factors of the length of the vector that, that's in the corresponding basis element. So I can write this as inner product of u and v1 and the inner product of v1 and v1 times v1. Right, the same thing for V2 and the same thing for V3. So now we've got an expression for how to write any vector u that we're interested in as a linear combination of the elements of our orthogonal basis. And it looks very much like what was in the previous theorem, but the only thing you've got to keep in mind is that you actually got to divide by the squared length of all your basis vectors in the coefficients, right? And if your basis was orthonormal, the special case where it's orthonormal, all those inner products in the denominator are 1, right? So this is sort of a slight generalization of what we just proved. So if you crunch out, now there's not 3 inner products, there's 6 inner products, but you just sit down and crunch them. What do you find? You find that at 0 V1 plus a half V2 plus 3/6 V3, which is a half, obviously. So the coordinate vector is coefficient of this one, and this one, and this one shoved in a in an R3 vector. And so that is the coordinate vector of u with respect to b. Okay, so the answer is A. Does that make sense? Yes.
Sorry, could you explain how you go from line 1 to line 2? Is that just linearity?
So line 1, like this here.
Yeah.
So that's just because of the definition of length.
Right.
So the length of v is the square root of inner product of v with itself. So if you've got length of v times length of v, that's just the inner product of v with itself. Yeah. So just definition of length. Okay, any other questions? All right, so this is a really useful trick. So it's sort of saying that the thing we actually proved you can easily generalize to the case where they're not normalized. And sometimes that's more convenient, right? Because why? Well, because when you normalize things, you get a bunch of square roots everywhere, and sometimes that's annoying. Sometimes it's not. Depends what you're trying to do. But if you feel like it, you can play with the unnormalized version instead, as long as you take care of the factors appropriately. Okay. So, yes, the answer was A. All right, now, there's really two really fundamental theorems in this section. So one of them I've already mooted, which is Graham-Schmidt. And Graham-Schmidt says that every finite dimensional inner product space has an orthonormal basis. Okay? So we haven't proved that yet. Might not be obvious, but it's true. Every finite dimensional inner product space has an orthonormal basis, and we'll prove that by actually constructing one. But what I want to state first is just as important, and it's called the projection theorem. And the projection theorem says that if you've got any inner product space you like, okay, so let V be an inner product space, and you take a subspace of it, W, And let's assume that the subspace W has an orthonormal basis, or actually just an orthogonal basis. Now, if Gram-Schmidt's true, then every subspace is going to have an orthogonal basis. But let's not put the cart before the horse. Let's just assume there's an orthogonal subspace, an orthogonal basis for W. Then the claim is that everybody in V can be written as something from W plus something from W perp. Okay? Everything in V, if you've got a subspace W, it's got an orthogonal basis. Everything in V can be written as something from W plus something from W perp. Remember, W perp is just the set of all the vectors that are orthogonal to all the vectors in W. Right? And moreover, the thing that lives in W looks exactly like this. Okay? So this is what we want to prove. This is the projection theorem. Now, we give this thing a name, and the reason it's called the projection theorem is that we give this W. So you take any U in the space V, you can find this unique vector W, which we call the projection of U onto W. And it's the unique thing that when you write U as a sum of something from W plus something from W perp, it's the unique thing that lives in W. Okay? Now, we're going to find that this thing has lots of nice properties. In particular, one of them is that it's the closest thing in the space W to the vector V. To the vector U. Right, that's one nice property it has. Let you guys read that one at home. This is the more interesting one. So if your basis happens to be orthonormal, then all of these things in the denominator are just 1, and you get this even nicer looking thing. Okay? So this is sort of the nicer looking version of the projection theorem. So you can if you normalize your vectors to start with, you can just scrub out the denominator. Okay? All right, let's prove this. So the first part, it's kind of one of these proofs where you need to pinch yourself and wake up for the next 2 minutes just to convince yourself I've actually done something. So let's take the vector that we're interested in, U, and let's take this thing W that we've made out of U and our basis for W. I'm going to prove the general version for an orthogonal basis. If you actually normalize properly, just forget about the denominator because it's 1. Okay, so we've got U and there's W. Now clearly, W lives in the space W because it's a linear combination of the basis vectors for W. So the question is, what's W perp? That's what we've got to find, right? We've got to find what W perp is, the bit that lives in big W perp. Well, we actually know what it has to be. It's got to be U minus W, right? Because I want W perp and W to add up to U. So clearly, W lives in W. And U is the sum of W plus W perp. So it looks like we're done. But we're not. What do we still got to show? There's 2 things we've still got to show. What have we got to show? Sorry? Uniqueness. We need uniqueness. But there's even one thing we've got to prove before we get to uniqueness. Yeah. We still have no idea where W perp lives, right? So the first thing that we've got to show is that this thing lives in W perp. So what does that mean? Well, it means we've got to take an inner product of W perp with anything in W and show that we get 0. But you'll prove on the problem set that it's actually enough to show that all the inner products with the elements of a basis, an orthonormal basis or an orthogonal basis, are 0. Right? So if you've got this vector W perp, if it's orthogonal to all of the VI's, then it's orthogonal to any linear combination of those VI's just by linearity. Okay? So it's enough to just consider orthogonality with the basis elements. So we just need to take the definition of W perp, which is U minus W, and take the inner product with VI. Linearity says this is inner product of U and VI minus inner product of W with VI. This is the inner product of U with VI minus, let's shove in the explicit expression for W. So you've got the sum over J, 1 up to K, U, Vj, length of Vj, Vj. So that's W. We want to take the inner product of that with VI. Okay, now all of this stuff sitting here might look complicated, but it's just a scalar. It's just the ratio of two inner products, so it's just some scalar. So we can use linearity in the first argument. So I can drag out that J sum, and I can drag out that ratio of inner products because, again, they're just ratios of scalars. What I'm left with is the inner product of Vj and Vi. But fourth or fifth time, I've lost count now. What's the inner product of Vi and Vj? Well, it's 0 if j equals anything other than I. So the only term in this sum that actually gives you anything other than 0 is when j equals I. And then what do we have? Well, it's just the j equals I term. And what does the j equals I term look like? It looks like this. And lo and behold, you got the same inner product upstairs and downstairs, so they cancel. And you just have the inner product of U and Vi minus the inner product of U and Vi, which is 0. So what that tells you is that W perp is orthogonal to everybody in the basis for W. So it's in fact orthogonal to everybody in W, which means it lives in the space big W perp. Okay? So we know where this little vector W perp lives. It lives in W perp, the space big W perp. So what do we still need to do? We still need to worry about uniqueness. Right? So what we've got so far is that you take any vector in V, in the space V, you take any vector in there, you can write it as this thing W that we wrote down, plus, which we call the projection, plus something that lives in W perp. Okay? So the last thing we want to show is that this is the only way you can do that. Right? There's not some other W that'll work. You have to use this W. Okay, so to prove uniqueness. What do we do? Usual argument. You suppose there's some other way of doing this. So let's suppose there's some other way of writing U as a linear combination of something from W plus, or the sum of something from W and something from W perp. Now, what does that mean? It means that this V plus V perp thing equals W plus W perp because they both equal U, right? Remember, we know what W and W perp are. They're the things that we just wrote down. Okay. Now, if I just stare at this, I can take W over to the left and V perp over to the right. Now, why is that equation really interesting?
Because it involves the equality between a vector from one space and another from its curve. So, but only the zero vector is the intersection between the two vector space.
Yes, that's exactly right, right? So because W is a vector space, we know that the left-hand side lives in W, right? Because both pieces live in W, so their linear combination lives in W. So V minus W lives in W. And W perp is a subspace. So W perp minus V perp lives in W perp. So V minus W lives in W perp, because V minus W equals W perp minus V perp. Okay? So the left-hand side lives in both W and W perp. And the right-hand side lives in both W and W perp. And we know, you'll prove this on the problem set, but it's basically exactly the same proof that we used when we were talking about Euclidean space a few weeks ago. We know that the only thing in the intersection of W and W perp is the zero vector. Okay? So we know that V minus W is in both W and W perp, and that's 0. And that implies that V equals W. And therefore, either using exactly the same argument again or just using star, that tells you that V perp equals W perp. Okay? So we have uniqueness. You assume there's a different way of doing it, but you find that V equals W and V perp equals W perp. Okay? So there's only one way of playing this game. So the thing that we wrote down and called the projection is quite a fundamental relationship between the vector U you're interested in and the subspace W. It's the unique thing in W that lets you write U as something from W plus something from W perp. Okay. So this is the Graham-Schmidt theorem. Now, I won't prove this now because we don't really have the time, but we can do it tomorrow. But what I will tell you is the proof is basically a question of staring at this algorithm and seeing why it makes sense. So this is the Graham-Schmidt algorithm. And the Graham-Schmidt algorithm is a recipe for converting any old basis at all, right? Any old basis at all into an orthogonal basis. And once you've got an orthogonal basis, you just normalize it and you've got an orthonormal basis. Okay, so what's the recipe? So who's seen Graham-Schmidt before? I can never remember who's. Is this covered in 1030 anymore? No, all right. So the idea is reasonably straightforward. We start off, so we're making the V's. We're choosing these V's, right? So we start off by saying, all right, V1 is just U1. And then in a perfect world, we'd be able to say, all right, V2 is equal to U2. But that's not going to work in general because what we want is that V1 and V2 are orthogonal. So what do you have to do? You've got to pick something that is orthogonal to U1. So what does that mean? Well, it really means you've got to pick something that's in the perp of the span of U1. And if you look at what this thing is here, this is precisely that, right? This is U2 minus the projection of U2 onto W1, where W1 is the span of V1. Okay? So you choose V2 to be basically U2, but you've got to subtract the bit of U2 that's poking in the U1 direction. Okay? And then you do the same thing for V3. You let it be U3, but you subtract off the bit of U3 that pokes in the V1 direction and the bit of U3 that pokes in the V2 direction. And then you let V4 be U4, but you've got to subtract off the bit of U4 that pokes along V1 and the bit of U4 that pokes along V2 and the bit of U4 that pokes along V3, right? Because you want to recursively make something this basis such that the ith element that you're constructing is orthogonal to all the previously constructed ones. Okay? And there was nothing to do here because you hadn't made any yet, so there was nothing that you had to demand that V1 was orthogonal to. So V1 can be whatever you like. V2 is U2, but with the projection subtracted so that it's orthogonal to V1, yada, yada, yada. Okay? So it's not, what's not clear yet, it is clear that these things are orthogonal, I think. What's not entirely clear yet is why they're actually independent. Right? Why you get an independent set by doing this. But we'll talk about that tomorrow. Okay. Thank you for your attention, and I'll see you tomorrow afternoon. Actually, one final favor, if I could ask you. I'm playing around with how many polls we're asking in the lectures. So I'm going to do something slightly different tomorrow. But just as a control sample, can you answer the poll that I just asked? It's not a maths question. It's just